When we're talking about galaxies, we've talked about spiral galaxies, elliptical galaxies, and we've talked about a variety of other kinds of galactic structures, groups of galaxies, and so forth. The book then talks about active galaxies, in particular active galactic nuclei, because really that's the part of the galaxy that's active. I mean, you could say a starburst galaxy is active in terms of creating stars, but when we talk about active galaxies, we're mainly talking about the nuclei. First incidences or observations of active galaxies go all the way back to the 1940s when astronomer Carl Seifert was looking at a variety of galaxies that had particularly unusual cores. These cores were very small, they were very star-like, just dots in the middle of the galaxy. What often happened was that you tried to overexpose the galaxy and to get the core, or you try to get the galaxy's overexposed. The cores themselves are just super tiny. The best telescopes, they just look like dots. So I mean they're pretty small. They almost 30% of the light comes as emission. So examples here of some of these galaxies that we now call Seifert galaxies. And then most Seiferts are spiral galaxies. And so we have these extra bright. So here's an example, NGC 10868. And on the left is what it looks like if you do a much shorter exposure. You get the picture on the right. The picture on the right shows you primarily just the core. The other exposure, the core is overexposed on the left, but you get the outer parts of the galaxy. With the Hubble telescope, we're able to get closer up views to some of the Seifert galaxies. So the Seifert galaxy NGC 4151, when we look at it with the Hubble telescope, we see jets of material spewing out of the core. And we see evidence of gas circulating in here. And so what is that suggesting to us? Well, we've seen that with other galaxies. That suggests something, a lot of mass in a very small area. So that sounds like a supermassive black hole. Well, we talked about the Eddington limit several times. The Eddington limit is how bright something can be and still be shining without the light pressure pushing away all the mass against gravity. So you can actually calculate the Eddington limit as to the brightest something can be, and the brightest it can be depends on how much mass it has compared to the luminosity and mass of the sun. So if we rearrange that equation and solve for the mass, then that would tell us how much mass is associated with something that is as bright as we see, assuming it's close to the Eddington limit. Could have even more mass than that. But the masses we come up with are millions of solar masses, and they're in very tiny little areas. So that suggests, in fact, that we are looking at a Seifert galaxy. Extreme Seiferts we call N galaxies. And here's a very famous, pretty example of an N galaxy right there. So Seiferts, supermassive black holes. M87 is another interesting galaxy here. Has an active core. And when you look at M87, you see there's a jet of material coming out of the core, primarily hydrogen. Again, this sort of thing with accretion. So it suggests that something's accreting in there. The energy of the jet gives us a rough idea of the mass that's accreting. And in this case, M87 is a giant elliptical galaxy. It's a CD galaxy, so it's right at the core of a giant star cluster. This is giant elliptical galaxy. The supermassive black hole in the middle seems to be about 3 billion solar masses. That's much bigger than the solar mass, much bigger than the supermassive black holes of galaxies near us. Again, suggesting that maybe the CD galaxies or the supersized ellipticals in the core of these large, rich clusters are mergers of other galaxies. So you could merge all the black holes. The jet here is interesting because with the Hubble telescope, we can actually look at gas on either side of the jet, And when we do that, we see one side is very much red shifted, the other side is very much blue shifted. Again, that suggests that gas is swirling around at very, very high speeds. Well, by measuring the red shift and the blue shift, we can find the velocities, and by figuring out how far out it is, we can then figure out the mass. Again, we end up with billions of solar masses. Interesting thing about M87 is that in 2019, April 2019, a radio telescope organization that called itself the Event Horizon Telescope was able to image what may be the accretion disk around the object at the center of M87. And what we see is we see the accretion disk here surrounding pretty much nothing. And so again, this is strongly suggestive that what we have in there is a supermassive black hole. Interesting thing about that jet. When I was in college, there was this huge mystery around that jet out of M87 because it looked like the jet was going faster than light. Well, it can't go faster than light. What happens is the jet is moving at about 5/6 the speed of light. That's really, really fast. But that means in 6 years, it's gone 5 light years. Okay, well, because it's kind of going at an angle, the jet would have been there, and so light would have traveled a certain distance to us, but after 6 years, it's over here, and so light actually travels 4 years less to get to us. So that means that after 6 years, the light really is only arriving 2 years later than it was at the first spot. But that's 3 light years over. So it looks like light went 3 light years in 2 years. So they call that superluminal motion, faster than light. It's not faster than light. It's an optical illusion that's entirely due to the orientation of the jet and so forth. So that's the solution to that mystery. So sometimes you might be reading somewhere online about faster than light travel. You still can't go faster than light, and this is one thing that people that don't know any better often list as something going faster than light. And it's not. It's really just our illusion as to how it